Great. All right, let's give this a shot. All right, so today we're going to be talking about conditional probability. And statistical independence. So you all watched the video about statistical independence and the Challenger disaster with the space shuttle. I was in kindergarten when that happened, and it was like kind of the first thing in the news that I was like, wow, there's stuff going on out there in the world. It's kind of like, you know, you're a 5-year-old, you're not really paying attention to what's happening. But I remember that being a thing. Everyone was sad and devastated. So in that video, we learned about independence and how engineers can think about how things are related or not related. So we'll talk about how we can use statistical independence to calculate probabilities and to evaluate whether or not things are in fact independent. So that's a real important thing to know. So last time, this conditional probability, statistical independence, is going to be picking up from where we left off. On Wednesday, we talked about some basics of probability, so just a quick review. We talked about sample spaces, and we started to get some Venn diagrams up in there. So our sample space, which we typically call S, we know that some event can occur within that sample space, and we'll just call that A. And we know that the probability of A is going to be somewhere between 0 and the upper limit of probability, which is 1. So total probability always adds up to 1. Love to get into some advanced probability where you're looking at more than 1, but you guys give it 110% in engineering. Your probability, we only give it 100%, all right? So just keep that in mind. So A will fall somewhere between 0 and 1. And then what do we want to, if we were to calculate the complement of A, which we call A bar or not A, what's that probability? Just 1 minus probability of A. Okay, so we're getting some, building up some basics here. And then we learned about mutual exclusivity. So if I throw in another event here, B, and they're not touching, they're not intersecting, they can't happen together, then the probability of A or B is just going to be the addition of those two. So this is what we call the addition rule. Really, really advanced rule there. But it does get a little more complicated when they are not mutually exclusive. So here they are ME. But if they're not ME, meaning what? They overlap, they intersect. Then what is the new probability? Probability of A or B. So we can add them together, but we don't want to double count that overlap. And we talked about how if this is A and this is B, and they're not mutually exclusive, they intersect, there's going to be 2 layers there to that relationship. And we're going to subtract out one of those intersections. And when we talked about the flaws in the cans, you can have a top flaw or a side flaw. What's the probability that there is a flaw? I had written one flaw down, but what's the probability that there's a flaw? Well, we can have a top flaw, a side flaw, but we don't want to have 2 of the top and side flaws. So we're going to subtract one of those intersections out. So then we get, which I'll just color as this outline here, we get this 2-dimensional shape that looks like this. That represents A or B, but doesn't double count that little overlap there. So this is the general multiplication rule. Okay, so now we're going to get into some kind of general addition rule. Yes, because I'm going to talk about the multiplication rule. Thank you.
And one of the things, it's like P A, P, that's A but not B.
Right here. Oh, this right here.
Yeah, like P and then just say A N.
This is P. Yeah.
Yeah.
So we introduced that symbol, and then I kind of quickly got rid of it. That's A and B. So that's where they intersect.
So it's the same.
Yeah. So good clarification question. So that little intersection right there is probability of A and B, which is the same as saying AB. And I'm just going to be writing it as AB for convenience here. Okay. So we're going to get into the multiplication rule today, which gets at how do you treat this intersection when you have numbers and you want to figure out what is that intersection. This is when the multiplication rule comes in. Okay, so let's get into the new stuff. I'm gonna get this a little bit closer here, since that's my microphone. All right, so we're gonna be thinking now about our sample space and how that could change over time. And I'm gonna give you a table here that we used last time, where we had samples. Samples of aluminum rods. And we had rods that were either too long or too short or okay. So too short. Okay, and too long. And then we had our diameter over here where we had too thin, okay, and too thick. So let's divide this up. All right, and I'll just drop a couple more lines here. Great. Okay, so the numbers that we had here from this sample is we had 10, 3, and 5. We had 38, 904. And then 2, 25, and 13. Don't want to erase the whole thing. Okay. That's okay. So what we're going to do now is think about subsets of these sample spaces and demonstrate some concepts here. When we're thinking about a subset of a sample space, we're saying, okay, well, what if I pick a bolt and it's too short, let's say. Well, now I can ask some other questions about probabilities of the diameter based on this subset of too short bolts. And so now we're going to kind of adjust our sample space based on that. So first of all, let's just go back to this. What's the probability that a randomly selected rod's diameter is okay? Okay, so here's the diameter, okay. Let's go ahead and look at these. And so we get 928 over 1,000. Okay. Now let's select the diameter. We find out that the diameter is okay. What is the probability that the length is also okay? So now we're asking this question out of a new sample space, which is this 928 over 1,000, or 928 thousandths. So our new sample space, so S, we'll just call it S naught, is equal to 928 instead of 1,000. And we said, okay, what's the probability that the length is okay? So probability that length is okay, given that we know that the diameter is okay. So now in our new sample space, we're just going to divide this length okay, so that's going to be 900 divided by our new sample space, 928. Hopefully that makes sense. And we'll calculate that new probability, which is 0.97. Okay, so not too bad so far, right? But what we've done here is we said we now have kind of a condition. We said we know some information about our sample or experiment. We have a conditional sample space, and it really is just a subset of that sample space. And so the way we write this is we're just going to say probability that length is okay, and then we do this long line that means given D is okay. So another just kind of short, so maybe like A given B. And this is what we call conditional probability. And this can be really powerful in so many things because it's like, well, if we collect some information or we make an observation, we can kind of shrink the world of possibilities down and then calculate a different probability based on that new information. Okay, let's look at a different example here. I'm just gonna erase this stuff. All right, so now I'm gonna get the highlighter out. Let's try this out. We're gonna look at the probability that the diameter is okay if the length is too long. So here is our new subset. So length is too long. And then we want to say the diameter is okay. And we're going to just do a different color here. Okay, so probability that diameter okay given length too long. And then we can just kind of add this up. We'll just do this really intuitively. So probability that the length is too long is 2 plus 25 plus 13. And that's going to be in our denominator. In our numerator, the probability that things are okay. Well, we can really only use this okay diameter okay part because we're in this too long sample space. So we're not going to look at these numbers. So it has to be 25. So now we're using kind of a smaller subset here within the too long sample space. Okay, so that's kind of how to do it intuitively, and that's going to be 25 over, let's see, 38, 48, 50. Nope, 40. 25 over 40, right? But let's think about it this way. We have in the numerator, this is the probability that it is too long. And because it's really the intersection, right? And diameter is okay. So we're intersecting the two sample spaces. Diameter is okay, and bolt is too long. So that's the intersection right here. All right, and then in the denominator, we have probability that it's too long. So to more generalize this, we can say that this diameter is okay, we'll call that A, and too long, we'll call that event B. This is really just the probability that A given B is going to be equal to the numerator, probability that too long, that's B, and A, so B intersect A, divided by the probability of B. And this is the conditional probability rule. Now, what we'll find out in a minute is that I wrote it too long and okay. You can also write it this way, probability of A and B divided by probability of B. So these two are always equal to each other. All right, so just to put a Venn diagram to this, we've got two events, A and B. We just said that, well, we got some information and we know that B exists. So we're in this B world right now, this B sample space. So this is, if this is S, this is going to be S naught, our new sample space. And now we're interested in finding the probability of A, given that we're in the new sample space B. So this is that intersection, but we're dividing by this total new sample space area. Okay, so this leads us to another concept we're going to mathematically explore: statistical independence, or probabilistic independence. So independent events. So how would you describe something that's independent, statistically independent? What about something makes it independent from something else? A is independent of B. There's no like linkage, there's no information. Yeah, A happens, B happens. They don't really talk, right? They're kind of mutually exclusive. They may not be mutually exclusive, but they're not influencing each other. If A happens, if the problem A happens, the probability of B happening doesn't change. So the knowledge of one event occurring, I'm just gonna type this out, I'm gonna get a little bit bigger here. We'll just say the knowledge, come on now. Of one event occurring does not affect the probability or knowledge, right, of another event. Every year I struggle with occurring. Nope. 2 C's, 1 R. Let's see. There we go. Nope, still not it. 2 R's, 2 C's. Okay, we'll go with that. All right, so in the Challenger video, there was an assumption that the O-rings were independent, right? If one O-ring fails, maybe another one won't. But what did they find out about the O-rings in the Challenger and the booster rockets? They found out they weren't independent. Does anyone remember why? Like, what they kind of had a little snippet on it. What was going on with that? Yeah. Just like the mechanism of it. It's like the way the thing was bending that they would fail together. So I was like, dang, apparently it wasn't redundant. Redundancy, I guess if you think about it from an engineering standpoint, redundancy should mean that if something fails, it's not going to influence the outcome of the redundant mechanism, right? It shouldn't. They should be independent of each other. So from a statistical standpoint, redundant mechanisms shouldn't fail together. They should be statistically independent. What would be an engineering example, like a civil engineering example of statistical independence and redundancy? A car, guardrails? Okay. So a guardrail is supposed to do what? Okay. So maybe so you have guardrails, that's one mechanism, and there's a redundant mechanism, maybe of what's that? Okay. Yeah. A little extra space or another mechanism. Um, I don't know, like I guess we build foundations to withstand, safety factor of potential failure mechanisms. I don't know if we have maybe like in steel design, you put like redundant bolts in and yeah, what do you think?
When the environment's design, except basically.
You always have an extra tank. And the tank, this tank's full, you have that tank, right? They're not gonna, yeah. I'm thinking of like natural disasters and power plants and earthquakes, right? Like there, there's maybe some safety mechanism over here, and if this one fails, hopefully this one doesn't. Like, sometimes it's hard to make things redundant, but we can put more capacity in, we can build more space, we can do safety factors and things. Yeah. So some examples of things that may or may not be independent. Okay. The number of vehicular accidents on a snow day. I think those are independent or not? No, probably not, right? There's a mechanism there, slick roads or poor sight. Okay. The Cleveland Browns winning the Super Bowl and the number of lightning strikes that happened that season in Cleveland. Independent. Unless the other team got zapped. Okay. Very low probabilities of that. Okay. Great. So do you think we can figure out if something is independent or not? Is there a mathematical test? That's a leading question. How would we test for independence? Well, we just actually learned a couple of things here that will help us. So let's just take a look at that. Testing for independence. So we can mathematically test for independence. And so let's look at the conditional probability rule. So probability of A given B is going to be equal to the probability of A and B divided by the probability of B. So if you think about the conditional probability rule, if B occurs and A and B are independent, should the probability of A be impacted by the fact that B occurred? No, it shouldn't. So in this particular case, we know that this is kind of like not independent, right? If and only if the probability of A and B does not equal the let's see, probably okay, A given B. So if that is something, then we're gonna look at probability of A. Actually, Control Z does not equal the probability of A. Okay, so B occurs. What's the probability of A given that B occurs? If it's not the probability of A, then we know they're not independent. So they should influence each other. So let's look at the bolt thing. So the probability that we have too long, does that equal the probability that we have too long given it's too thin? Are these independent or not? So probability that it's too long is equal to 40 over 1,000. Let's just go back and look at that real quick. Okay, so too long was 40, too thin is 50. Okay, so let's just look at that. Okay, too long, and then probably that we're too long given that we're too thin. I'm gonna just go back over here. So given that we're too thin, given that we're too thin, too long, so that's 2 right there where they intersect. So that's 2 over 1,000. And then we're going to divide by that sample space, which was 50 over 1,000. So this is the too thin sample space. And that's the intersection of the two. So that equals 2 over 50, which is 0.04. So these values end up being the same. And at least from the data standpoint, we could say that they are independent. Is it just a coincidence that they both are the same? Maybe you got to kind of dig a little deeper to figure that out. But from this numerical standpoint, the probability that A given B is in fact equal to the probability of A. So let's just generalize that real quick. Let's say 2 events are independent if, so 2 events A and B, probability of A given B is equal to the probability of A, or the probability of B given A equals the probability of B. So that's the way we can test for that. Okay, so now we're gonna get to the multiplication rule, which we said we would get to. And this comes from the conditional probability rule. The idea is we want to find what is the probability of A and B. And we're going to basically just rearrange the conditional probability rule to find this out, figure out what this is. So the conditional probability rule said the probability that A given B is equal to the probability of A and B, all over the probability of B. So we're just going to rearrange that algebraically to solve for this. So just bring that B over, probability of A given B times the probability of B. If they are not independent. But if they are independent, what is the probability of A given B? Nolan, what's another way to simplify this particular term right here? Yeah,
Um, if they're independent, just put down.
exactly. So if they're independent, probability of A given B just equals probability of A. So we can write that if they are independent. Probability of A and B is just equal to the probability of A times the probability of B. So very simplistic here, like, wow, why do we need to go out of our way to define this multiplication rule? But this idea of statistical independence that we can just multiply individual probabilities together, that's what they talked about with the Challenger video, is that, well, if we know the probability of failure of one thing is this, we're assuming they're all dependent, we can just multiply those probabilities together to find the total probability of them all happening. So in the case of the O-ring failure, there were 6 O-rings, and the probability of failure of one ring, of just an individual ring, was equal to 0.03 or 0.003. I can't remember exactly. Let's just say 0.003. And they're like, well, they're not all 6 going to fail together, right? What's that probability? So probability that all 6 fail, assuming independence, would be probability of O-ring 1 fails times the probability that O-ring 2 fails times the probability that they all fail, right? So this just simply equals, since they're all the same, 0.003 to the 6. And you can see when you have small probabilities that very quickly it can become a very tiny probability. 0.003 to the 6. 7.29 to the negative 16. Okay, so if we have a low probability of failure, that probability that they're all going to fail together is extremely low. So maybe someone would be like, it's great, we're good to go. But that's only if they're independent. If they're not, then you're in this world, right? Where if B happens, then all of a sudden your sample space has shrunk. You've got a lower denominator, and so you could potentially have a higher probability of something happening. So important to keep in mind. Okay, let's do an example of conditional probability. So we've got 2 power plants in a city, and we have power plant A and power plant B. Each can power the city. On their own. During what we'll call just like base load, not peak load. Both are needed for peak hours. And then during peak hours, if one plant shuts down, we get a brownout. If both shut down, we get a blackout. Okay. So on a given day, the failure of A, so we'll just say let A be the failure of plant A. And on a given day, the failure probability is 0.0, or shutdown probability 0.05, kind of high. But. And then B, failure of plant B. And that's a little bit higher, 0.07. Maybe it's a little bit older, something like that. And then finally, just from historical data, we know that probably with A and B, the both failing is equal to 0.01. Okay, so first question for you all. Are A and B independent? How can we find out? What are the new tools that we have here? Yeah, that's kind of like the conditional probability. So what we can look at is using conditional probability. So A given B, is that equal to the probability of A, or vice versa, probability of B given A equal to the probability of B. Alternatively, we could look at, I think what you're getting at is probability of A and B. Is that equal just to the probability of A times the probability of B? So that's another kind of test we can use for this. So we don't know A given B right now, although we could probably figure that out. But we'll go with this method right here, since that's going to be pretty easy. So we already know A given B, they gave that to us. So 0.01. And then we'll just multiply 0.05 times 0.0. Oh, sorry, that was supposed to be 5. 0.07. So from the start, we kind of realized that they aren't equal, so they don't fail independently. We could also look at these relationships, but we'll do that in a sec, a little bit differently. Okay, so now the second question: if one of the two units or two plants fail on a given day, what is the probability that the other will fail? Okay, so first we're going to write it out. Take a minute or just a second or two to write out what is, let's just say, if one of the plants fails. So probability of A, so we know that one of them fails. We're just going to say, so A happened. What is the probability that B will occur? So write that out as a probability statement. So we said A occurred, so A is given. What's the probability that B will happen? Probability B given A. And then we're simply just going to use the conditional probability rule. we said A occurred, so that's our new sample space in our denominator, and then we're going to use the intersection of the two up here. So that first probability was given. Second probability we already also have. So we actually have a pretty high probability of B failing if A failed. So maybe, you know, there's like a huge load on the system, and I don't know how power plants work, but they had to shut it down. All right, and then let's look at the alternative. If B failed, what's the probability that A would? And notice how I can interchange A and B in this intersection here, and you're going to get the same probability. If A intersects B, based on the Venn diagram, it should be the same area as B intersecting A. Okay, so we can see that there's a little bit of a different influence here based on the individual probabilities. So 20%, I don't like that. If A goes down, what's the probability that B will? So B is kind of like this loose cannon here. We got to check out what's going on with B. We don't want it to have a 1 in 5 chance of failing. All right, so now the third one we'll ask is what's the probability of a brownout? So we defined a brownout as either of them going out. So either A or B fail. So probably A or B. And this is getting back to that generalized addition rule. Probability of A plus the probability of B minus their intersection. We know that they have an intersection. We know that they're not mutually exclusive. Okay, so about a 11% chance of a brownout. No, I don't want to live there either. We got to work on this. Sound like Texas over here. It's cold and everything just shuts down. Okay, so in the limited time we have left, I want to introduce one more concept here, and it's what we call the theorem of total probability. So we're going to use an example here to illustrate it. And we've got a town that's downstream of a mountain. And depending on the snowpack of that kind of winter and spring season, there's a certain probability of flooding occurring in the river. So flooding is just going to be like the water gets above a certain elevation and floods a neighborhood or whatever. So we're going to define some events here. We have F is flood occurs, the river gets high enough. We're going to have H as heavy snow. And maybe that's like, oh, it's 80% or 80 percentile and above or something like that. We're going to have N for normal. Maybe that's between 30 and 70% or 40 and 70%, something like that. And then low is low snow. L is low snow. So we're going to draw the Venn diagram here. And before we get into that, let's just look at this here. So we've got the snow, and we're going to draw the sample space for snow outcomes, heavy, normal, and low. Does that cover all of our bases here? If I gave you the numbers, maybe that'd be a little more illustrative. So the probability of this is 0.2, the probability of medium is 0.5, and then low is 0.3. Sounds about right. So all of these add up to 1. So that means that we can call this collectively exhaustive. And the idea of collectively exhaustive is that we can define events that span the entire sample space. So the way we would draw this is, let's say we've got a little bit for heavy, a lot of it for normal, and then a little bit left over for low. So H, N, and L. And then within that, we're going to intersect this flood event. So I'll give you some new probabilities here. The probability of a flood given heavy snow, do you think that's high or low? It's a little bit high. It's pretty high. So if we have heavy snow, we have a 90% chance. The probability of a flood given normal snow, and this can just be based on the record. You're like, okay, let's look at the snow record. Let's look at the stream record, runoff record. That's 40%. And then the probability of a flood given low snow is pretty low, but still not non-existent. Maybe it runs off really quickly, it heats up. So we're gonna draw this flood event superimposed, and it's gonna be a little funky. So we're gonna have a high probability in H, kind of a medium probability of an N, and just a little bit over there. So kind of a funky shape, but let's just represent the idea that we have very high probability of flooding over here in H, a little bit in N, and then very little bit over in L. And unfortunately, it is time, so I'm not going to be able to like fully go through this whole example, but if we want to find the probability of flooding, then that's going to simply be the sum of all these conditional probabilities times the probability of them occurring. So probability of flood given H times the probability of H. So all these conditional probabilities. The probability of flooding times normal, or given normal times the probability that we have normal, plus the probability of flooding given low times the probability of low. And to summarize this is we would just say the probability that an event A that intersects a series of collectively exhaustive, okay, so collectively exhaustive, and they don't intersect, they're mutually exclusive. Okay, so these events are collectively exhaustive, mutually exclusive. All we need to do is we need to sum up the conditional probabilities. So the probability of events, the probability of A occurring given the individual event, EI, times the probability that event occurs, EI. In this case, we have 3 events, H, N, and L, that are collectively exhaustive. And we're trying to find the probability of flooding. Okay, so we're gonna have to stop there, given our time. But I've got an example where it's a little bit of a different example where I go over this, and that is posted on Canvas. But we will pick this conversation back up and talk about Bayes on Monday, Bayes' theorem. And then I will be here to go over Python stuff for the next hour. So if you guys want to stick around, we can do that.